Well, hello everybody and welcome to another one of these geometry of pattern sessions. I'm your host, Kami Kiadai, and welcome. I'm sorry for doing it on Sunday at 2:51 p.m. Beautiful sunny day in Monterrey, Mexico, and today we're going to review some of the things we talked about last time and talk about the minimal triangle, and we're all going to use radians, so it's all going to come together. So join us as we have fun doing math. Wouldn't that be nice? So we're going to build up to these patterns. Pretty much this is where we're going to go today. Alright, but first I want to talk about what we saw last class. So I'm just going to imagine that you're actually following along with these. Pre-thing is that this is something that I've been working on. So I don't know what resource to guide you if you want more stuff, but if you're interested in like talking about it, hit me up and I'll send you a link to a Discord server where it kind of there's a conversation going. So again, review. So last class we saw the significant, I think, development of the star angle formula. So it's n minus 2k times pi over n. And this is the star angle formula. Of course, you can substitute pi by 180 and still get the same thing. But okay, so we got the star angle formula. So I always get asked this, what's k? So I always have a hard time talking about it, but it pretty much I always show them this and talk about how n is how many sides the polygon has and k is how many it jumps. But now think about it more in terms of mod. So in your calculator, there's a button there that says mod. Oh, by the way, did I zoom in on this thing? Wait a minute. So the zoom sometimes resets. Yeah, the zoom resets. All right. So, yeah, nobody's watching. All right, so we're talking about mod. So in your calculator, there's a button that says mod, and if you click it, you can pretty much do formulas around the clock kind of thing. So that means that if you have a clock, and well, that's not a good example. Let's look at the example of a pentagon. So if we have a pentagon, this is pretty much what mod 5 is. So that means that if we label these points, we go 1, 2, 3, 4, and 5, and then we say, well, if we add sort of the k now comes into play here, we're not going to worry about it too much, but if we can sort of do operations on this thing. So we can say something like, 1 plus 2 equals 3, 3 plus 2 equals 5, and then 5 plus 2 equals 2, 2 plus 2 equals 4, and 4 plus 2 equals 1. And so the way this works is that if you start with 1 and you add 2, you kind of go to 3. And then from 3, if you add 2, you go to 5. And then if you 5, you add 2, you go to 2. And then from 2, you add 2, you go to 4. And then from 4, you add 2, and you get to 1. So this is sort of how k works within this system. You can think of it in terms of mod, and k is just pretty much the steps. K is stepping, I like to say. There's probably a better way to describe it, but k is pretty much like adding or subtracting from any n, and mod will be the n, pretty much. So k subtracts or adds, it could do either one. So k, it's a kind of like a plus minus kind of situation. Because you can go backwards as well, you can kind of go like 1 minus 2, and then it goes 1, 2. So 1 minus 2, if we can go like that, 1 minus 2 will be equal to 4, and then 4 minus 2 equal to 2. 2 minus 2 would be equal to 5. And being fair, if this is true mod, if we were actually doing mod, these 5 wouldn't come up as 5. These 5s actually come up as 0. So there's no 5, there's actually just a 0. You can't go to 5. So it goes to 0, kind of looks better a little bit too. 0, this one's also a 0. And again, I'm sorry for doing these things. I know they're boring, I know they're awful, but I don't know why I got to do them. I don't know why. And from 0, we take away 2, we go to 3. And then from 3, we take away 2, and we go to 1. and then back it starts again, right? 1, 1. So you see how k can subtract or k can add. This is k subtracting, this is k adding. And so k is stepping inside of mod, and mod is what polygon we're working on. And the mod, the number inside of the polygon, the mod rather, is what n is. So it's mod n is the k, and k is what's stepping inside of mod. So k is sort of like the operator, or whatever number is happening inside of it. So it just so happens that if we have this system and we want to set up the shape of it, there are certain constraints for k. But k pretty much is this. K is stepping inside of n. Alright, beautiful, we're working on. So now with that out of the way, since we have sort of a definition, sort of, for what k is, now we can sort of, apply the star angle formula a little bit more. So if I were to say something like, well, just to be clear though, n is whatever polygon, rather like this. So n is any polygon. And then, dude, I'm just tripping out that this is fucking worthless. This class is whatever the fuck I'm doing. This is just, yeah, I don't know. So k is any regular polygon, and then we write n/k is any star polygon. Now the constraints for k, which we've seen a little bit, k has to be more than 1, and k has to be less than half of n. We've seen this before, but it has to do with the mirror symmetry of the shape. But we're not worrying about that route. We just want to, we've seen this before, so we just care about this. For now, it's all enough. So actually we can do away without this one. The real constraint is this one. Because when k equals 1, it's simply going to be the polygon. So this actually applies quite nicely to get the internal angle of a polygon. But just adding the k into the formula, we suddenly have the star angle formula. So k, any polygon, so this is the limit for k. K has to be less than half of n. So we can pretty much just plug in any number now, right? We can talk about the 10, 3. And then we can figure out pretty fast what angle it's in. Because k is 3, so 3 times 2, that's 6. So 10 minus 6 over 10. 10 minus 6 times pi. And so that's equal to 4 pi over 10. And the way we can explain this, or not explain, the way we can express it is that if we had a circle, we have pi, half a circle is pi, and we split that into 10 parts, so we can kind of cut it in half, and then cut these into fourths. So it's 1, 2, 3, 4, and 5, and then it goes again here. 6, 7, 8, 9, and 10. Little slices, we'll take away this, put it on top. So then this whole thing, this little half a circle sliced into 10 parts, is sustained pi over 10. Pretty much pi is divided into 10 parts. So 4 pi over 10 means that we're selecting 4 of them. So it's we're taking 1, we're taking 2, and 3, and 4. And that's the angle that this star has. Pretty much at every point. So it's this were a point of the star. So, interesting. And, it kind of helps to understand a little bit more of where we're going and what's happening. Because we can look at a pattern and then sort of see what star is happening, and we can sort of apply or plug in into whatever system we're working on the angle and correspond it to a different system, a different star polygon or whatever. And we could also install any angle into any pattern. It doesn't necessarily have to pertain to it, but it's usually done like that because that's the way it is. So we're going to take this away, and just to also we did a list last class, and the thing about that list now that I'm looking back at it is that I would have rather keep sort of an x value and a y value. Instead of having x on top, I would have x underneath. So it's almost as if I would have rather kind of step 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 goes on. But then under here, actually I should move this up a little bit, sorry. I'm not even going to do much of it, but 1, 2, 3, 4, 5, 6. Let's stop at 7 just because. And then under here I would write N1, N2, this little sequence is that we get a numbered, x value. And also nice is that we simply can use these numbers to get what angle each of these stars pertain, like what angle they're in. So for instance, this one is the polygon itself. So there's no polygon for 1 because again, if we plug 1 into this, we get, no, I'm not even going to do this over again. But yeah, so we start here, so it's like 0, 1, 2, 3, 4. I also like the way that it's ascending. So then we get this one over here, or rather we get the 0, because 4 minus 2, yeah, so here's a 0. 1, 2, 3, I'm going to take this away. I'm going to write it over here just because. So yeah, 0, 1, 2, and then here goes 0, 1. So every 2 there's a 0, so that's the way it sort of corresponds in this manner, right? So yeah, we don't get no 4. 4 starts at 9. But we get at least, the internal angle. So whatever we get on this list is what substitutes this thing inside of the parentheses. So these numbers, for instance, so if we wanted to know the internal angle of a heptagon, it's simply 5 pi over 7. And, same thing with each of these stars. So, it's nice. It gives us the internal angle of a polygon. It gives us the internal angle of any star that we choose. So, for instance, this one would be the 6-2 right here. So we could say that the 6-2 star has an angle of 2 pi over 6. What's interesting is that when we also apply these angles, we're going to find that they're going to come up several times. So for instance, 2 pi over 6, we can simplify that as pi over 3. So pi over 3 actually comes up. We can actually look this one up right here. Because we have 1 over 3. 1 over 3. So, that means that inside of this polygon there's a triangle just as much as inside of this polygon there's a triangle. And we can go up the list and several stars or shapes are going to repeat themselves. So there's also a pattern of which if the number has a common factor with how many sides it has. So that might also show up in several instances and in different manners, and also in factors of numbers. So for instance in 10, which is a factor of 5, so rather 10 has a factor of 5, has 5 inside of it. Like if you do the factor tree of 10, 5 is going to be in there. So it has that character to it. So in number analysis, not number analysis, but like studying numbers, you find that there's actually some sort of relationship between them. What's even more interesting will be that this is just the very basic numbers, and there's a whole list, this could go on forever, and there's no limit to how many sides that the polygon has or what angles we're going to work with. So, it just beckons infinity. Alright, so we review this, we saw the mod thing. Alright, that's good enough. I mean, at least for now, that sort of gives us an idea just to illustrate once more. We can do it inside of the pentagon. Very badly. Of course, it only works for regular polygons. Actually, I'm going to do it on the 7 since I have been doing a lot of 7 work lately. So we have 7 points, so this is mod 7. I'm not even do the additions. But if I say that we wanted to put in an angle, say of 7, 2, so it's like we're saying that, we're starting here at 1, 2, 3, 4, 5, 6, and 7. Well, 7, there's no 7, there's a 0. When we get to 7, it caps. That's sort of like the 0 point. And I should have maybe written down these numbers with a different color. Self-doubt is pretty crazy, man, honestly. So yeah, 7 points around the circle, I have them labeled, and so I start at 1, and I'm going to add 2. So in this case, k is going to be equal to 2. Mod 7 means that, well, n is equal to 7, and so we begin with this thing. So 1 plus 2, that's 3. 3 plus 2, that's 5. 5 plus 2, that's 0, because if it's 7, it caps. So 0 plus 2, that's 2. 2 plus 2, that's 4. 4 plus 2, that's 6. 6 plus 2, that's 8. But we're going over 7, so how much are we going over? 1, so 6 plus 2 in mod 7 is 1. And so we get the 7-2 star, and then we can ask the question, what angle is this? And we can look at our list, and this is a 7-2, right? Because mod equals 7, k equals 2. So this star is the 7-2. We look at our list, and there it is. So this angle right there, that's an angle of 3 pi. I'm going to take this away. 3 pi over 7. Interestingly enough, it just so happens that inside all stars are the lower stars. So that is to say that inside of this, well, it's amazing how many things there are to cover and how much I'm not equipped to teach these things, but at the same time, I gotta do it. Alright, so just as another example, I'm gonna do the example of, let's say we draw a polygon first. So if we draw a polygon, we're saying that this is an 8, so 8 inside of a bracket, an octagon. So what happens then if we extend the line? So this line just keeps going, and this line also keeps going, and they meet. And this line keeps going, and this line keeps going, and they meet. Oh, there's still something to go back to later, but we're going to see that in due time. But there's also the thing about half stars, but we're not there yet. So now we've extended the lines and they have a matching point. So if we can see that the line connects, and we see that now we have 8 new vertices, and they're going 0, 1, 2. So if we extend the 8, it extends onto an 8, 2. And we could apply the formula and get the angle of this, but let's keep this one more time going. So this extends, and this extends, and this extends, extends. Yeah, now this one's going like this actually. And so we have 8 new points around the circle, and so from the 8, 2 now we have the 8, 3. And again, we could find what this angle is using the formula. But what's interesting is how inside of a simple polygon, we can extend and get further. What's more interesting, I think, is that if we see an angle, if we see a star, that sort of implies that within it are all the lower stars. So inside of the A3, which is the highest it can go, you can actually see that if we kept these going, they now cross, and they don't match again with the radial line almost. Like now it's parallel to this line. So it's just going to keep going on forever. It won't converge again, which is also kind of interesting. That there's like a limit to these stars and how many points you can put in and how much, well, what kind of system you can come up with. So interesting, right? So inside of a star, we can also step back and sort of imply that within it are all the other stars. And so if we have a clue as to which this angle is, we also can infer what angle is before it. And from there, we can even infer what angle is before it. So if we have several points aligned, we can sort of use this system to find our way inside of a shape. And inside of that shape, we could, again, find some things which might help us sort of crack whatever point in a pattern we would like to crack and understand. So, interesting, stars nest, they're contained within each other, and so also the angles pertaining to the formula are sort of like contracting or expanding depending on which way you go, but you can just as well change this arrow and step back as much as you can go forward. So interesting, this is the 8, well guys, you see 8-3 is the last one, 8-2 is the red, and the 8 is the internal octagon. And if we wanted to, we can actually do the little business here. Let's do a little business. So we say that this is 5, pretty fast, no, actually 6. And so there's also the thing of, I'm having a hard time explaining this part, but I find it easier to just put in the number of whatever angle it is and just having the base. So for instance, this is base 8. So I could just write like base. I could just write base 8, which means that whatever number I put inside of these, they're always going to be around this. Further, I can imply that because it's base 8, it's dividing half a circle into 8, which means that any point on the pattern, say this, has to add up to double the base. So let's do it. So we have a 6 here, we have a 4 here. So any triangle is going to be equal to pi, so any triangle is going to be equal to 8. So we have this one's 4, and it looks isosceles. So this one's going to be 2, this one's going to be 2. It's so small that I don't know if you guys can see it. It's a damn shame. Alright, since this one's going to be like, complementary, I'm going to write 4 over here. There's a 4. There's a 4. Right there's a 2. Right there's a 2. Over here is going to be a 2 as well. All these are going to be the same. This one's also going to be a 4. And so because these are going to be equal to 16, 6 plus 2, that's 8, plus 2, that's 10, and we're missing 6. And now we're here, we're going to go to 2. And so this is 4, and this is 4, 2. So all these are 4, 4, 4, 4, and 4, around this point. So if we add them up, all of these have to add up to 16 because we're in base 8. And base 8 means that we're, again, if we're dividing, base 8 means that we're dividing half a circle into 8. So here's in 4. And this is base 8. So this is what base 8 means. So when I say 6, I'm talking about 6 of these slices. When I say 4, I'm talking about 4 of these slices. When I say 2, I'm talking about 2 of these slices. And so on. And alright, I think we're sort of getting there. And so it's sort of cool, really, to like substitute the angles onto a pattern and then try it, because it will add up. That's what's so cool about it. That they will add up and you can like have fun in, eventually some patterns will have like angles that are between. So it won't be like the even numbers, but they'll be like the odd numbers in an even pattern. So that's also kind of fun. Alright, I think this is, for now, we're going to do good. Just remember that. This is the most important thing to remember. Discovered last week, really cool thing, and yeah, we're gonna leave it at that for now. And so that's the review. So this is where we're at. So now we're going to talk about the minimal triangles. Part of me is like, maybe I should cater these videos to people so they watch them. Part of me is just like, dude, just do it, put it out there, go crazy, whatever. Like it'll fall into place in time. It's like, all right, boys, in my head, whatever you say. Minimal triangles, I have these 2 examples laid out, but I want to like first break down what these could mean. So we're gonna do again a list of polygons, but we're gonna break down their minimal triangles. So what is the least triangle, the smallest triangle we can put up that would create a polygon? So it just so happens. So I'm going to draw here a triangle. I'm going to locate its center. I'm going to suppose that's the center. Just imagine with me that that's the center. I'm going to connect this, and this is going to go down like that. I'm going to draw some more examples before I analyze it too much, but this is pretty much what a minimal triangle is. We're not going to break down the angles just yet, but that's what we're going to do pretty much. And we're going to stop in the hexagon. Actually, I should lay this out more so the floor is on the, like that. Imagine that that's a regular triangle, right? Alright, first thing that strikes you. What about all these have, what do all these triangles have in common? They have a right angle. So these are all right triangles. Alright, that's a cool thing to have in common. What else? Well, one of the angles is going to retain to being half of whatever the full spectrum is. What does that mean? It means that because it is the center of a square, it's pretty simple to sort of like, get this angle. Because it's the center of that polygon. And so how do we get it? Well, we can assume that whatever this is, if we actually extended these lines, so I'm going to do another color here, but if I extended these, it's pretty fast to like get what this angle is, because this is a full circle. And it's the center of that full circle division. I can put a circle anywhere, right? So a circle is 2 pi. So that point is going to be divided in 2 pi because it's a circle. And so this thing, which is like this, is going to be like 2 pi over 4. So like this angle is going to be 2 pi over 4. And so half of it, that is going to be 1 over 4. And so because now we're in base 4, and base pretty much like means that we're also dividing a triangle, because half a circle is equal to a triangle. So if we're in base 4 here, a right angle is going to be half of that. Half of whatever base you want is what a right angle is going to be. So this one's going to be 2. And this one's going to be 1. And I'm talking about that angle. So that angle's 1, that angle's 2. Let me take away some of these informations. 2 pi over 4, because again it's a full circle. Same thing here, that if we expand it upon this, we would get like this is like these, like that angle right there, that's a 2 pi over 3, which means that half of it would be pi over 3. So that's this pi over 3, that angle right there, because it's half of this, right? However, it just so happens, well, we're going to see this little case here, but what's happening is that if we're in base 3 here, this right angle can't be half. We can't half 3 and get a whole number. So whenever we have a base odd number for minimal triangles, we're going to multiply by 2. So if it's base 3, we're going to multiply by 2, and now it's going to be base 6. So if this angle was pi over 3, so again, this one is this one, 2 pi over 3. But if we're now in base 6, then this 3 becomes a 6, and this 2 becomes a 4. Because we have to make this, it has to state the same thing. So now if that's 4 and this is half, so that means that now this one's 2, that one right there is 3, this right angle is 3. And so we have to add up to 6. So 2, 3, and 1. So let's I'm going to do a little list here. What the hell? So do a little list here of the triangles that we've extracted so far. So we have this triangle, that's a 1, it's a 3, and that's a 2, and this is in base 6. So I'm going to write in base 6. Next we have the one from the square. This one's in base 4. Again, whatever number we have in base, it's what these numbers have to add up to. And every angle is going to be half of this. So in base 4, this is going to be half of 4 pretty fast. So 2, 1, and 1. Again, we're multiplying this times pi and dividing it by the base. So this angle is 2 pi over 6. This angle is 3 pi over 6. This angle is pi over 6. Pi over 4, 2 pi over 4, pi over 4. So 1, 2, 1, 3, 1, 2. And I'm also going to highlight really strongly here the center of my figure. So that huge red dot represents the center of the polygon. Alright, let's do now the pentagon. So pentagon is base 5. But we can't get our right angle, it's a whole number, if the base is odd. So we're going to go up to 10. And so if this angle, once more, so this angle is the same as this angle complete. So if we have half it, then it becomes the same. But just to be clear, that's 2 pi over 5. This angle right here, that's 2 pi over 5. That angle right there. Now we're in base 10, right? So this means that this denominator has to go up to 10, and this numerator has to go up to 4. So now this angle is 4 pi over 10, so half of it is going to be 2. So this angle is 2, that's a 5. And over here, that's a 1. Well, no, we have to add up to 10. So 2 plus 5 plus 2, that's 7. So this is a 3. So we have a new triangle here to add to our collection. That's red dot, again, symbolizes the center of our polygon. So I'd like to also exemplify, we're going to see that in time. But yeah, it's important to note where the center is. So here we have a 2, a 3. Well, I'm changing colors for this one. So this is, 2 pi over 5. No, over 10, sorry. 2 pi over 10, 5 pi over 10, and 3 pi over 10. If we were in base 5, we would get 1, 2.5, and 1.5. which is still valid. I mean, it's not wrong to put it in half, and actually will tie in nicely with Islamic patterns, because it will happen in Islamic patterns, for instance. See that? I don't know if you can see that, but that's a petal and a half. So it almost like suggests like we shouldn't get this into base double. We should stay in base 3 because that's what it means. I mean, there's still 3 slices there, you know, but it is a 1.5. So that's a 9 because that point is that point. Maybe I should no, I cut it. Yeah, but that point pertains to this point right here. So maybe it is better to not go into base 6. I'm thinking, I have to rethink my own definitions with this thing. But now that I'm looking at the example I want to show you, because it actually is a way to combine 12 and 9 using these minimal triangles, for instance, I'm going to have to retract and actually leave these in whatever base they're in. So I'm going to retract these and confuse you. I'm sorry, you guys, I'm sorry, but this is the way it's got to go. This is the way it's got to go. So we have to redo these. Yeah. So base 3. If I felt before that I was losing you, now I'm completely losing you. Now it's completely gone. Alright, so we have a 1 there. We have a 1.5. So let's put in 1.5. And over here would be, this is pi over 3, so that also would be 1.5. No, it would be 1. Simply 1. No, 2. Well, no, it'd just be a half. Because 1.5 plus 1, and this one's going to be just a half. So for the base 3, we have 1, 1.5, and a half. Yeah. Base 4, that sticks. Base 5 changes up a little bit. And we have here a 1, we have here a 2.5, and here we have a 1.5. Over 5, over 5, over 5. So it's pi over 5, again 1, 2.5 pi over 5, and 1.5 pi over 5. Yeah, very poorly explained today. I'm sorry, but this is... stop making excuses. That's what the voice says now. So yeah, we got that. So this is again going to be 1, 2.5, and over here is 1.5. So the suggestion would be, well, we're not getting there yet. Let's do one more over here on the 6. So this is actually base 6. So again, if we combine it with this one, we get 2 pi over 6, so half of it is 1. So the pattern is that all these minimal triangles have 1 at their center. You can see that 1, 1, 1. Yeah, this is better, right? Because we get to have that part of the pattern. To have pi over 3, 1.5 pi over 3, 0.5 pi over 3. And then base 6, we get to have 1, we actually get to put in here 3, and then there we actually get to put in 2. So base 5. And then we have here this pi over 6, 3 pi over 6, and 2 pi over 6. Yeah, that's pretty much it. And so these are the triangles. And what's interesting is how this one and this one are the same. And if we go actually into the 8th fold, we would get that. So let me look at the example of these two. What would distinguish them? So this is why I brought up this example and that example as I have there. Let me just repaste this. By the way, it wouldn't surprise me if nobody is watching and I'm talking to myself. Because even though this is mathematics, this is still, I don't know, tedious. I don't know, dude. Maybe sometimes the magic is not knowing, you know? Maybe it is sort of like breaking some kind of code by letting you guys know a little bit too much for nothing. Maybe it is just craziness, maybe it is just, I don't know, whatever, it doesn't really matter, it feels like work, like fun work, so that's why I keep doing it. Yeah, so we have these three minimal triangles, these four minimal triangles, and I want to focus now on the triangle for the hexagon and the triangle. So I'm going to erase everything and I'm going to rewrite those two triangles. And we're going to compare and understand how we could use them for different purposes. Even though they are still the same triangle, they will also sort of let us know what's happening. So I'm going to write in there minimal triangles for, I'm writing in the brackets 3 and bracket 6. And we're going to see how we get those patterns over there. So we're going to start with this one. So we said that that one was like this. This one has a 1.5, 1.5. This one has over here a 1, and over here we have 0.5. So in that pattern that I'm showing you, that pattern right there, that we call that the 912. And you're actually going to see these kinds of numbers combined. We can call the 912 or the 12-9. I think maybe it is better to write the 12-9 because 12 is higher than 9, I guess, whatever. So there's going to be a center of 9 and a center of 12 interacting. And what we can do is we can actually use this minimal triangle, that minimal triangle right there, to break down and find this pattern. And so the way we do it is that we can find factors of these numbers inside of this triangle. Now it's a little weird, but since we are in base 3, we can start to like question ourselves. You can begin to question again. This is going to be like pi over 3, 1.5 pi over 3, and 0.5 pi over 3. So we can start to think like, well, does 12 come into this place and does 9 come into play here? And actually, I've written this is not drawn properly. Rather, this would be like the short one. It looks a little bit like that. That's where the 1 is, that's where the 1.5 is, and this is where the 0.5 is. So it's kind of like slanted, so that's also what makes it different. And also what, yeah. So here's a 1.5 pi over 3, and here we have 0.5 pi over 3. So the idea consists now of pretty much like finding where we can put in 9. So we can put in 9 here, because if we divide this part into 9s, so if we take this base 3, we make it 9. We're not going to make everything 9. We could, but we can also see like what actually comes up as a whole number. So take for instance, like that's also a big part of the question as to what makes it tessellate. So let's make all of these 9. So if we put in a common denominator of 9, we have here pi over 3. We multiply that by 3 to get base 9. Almost, you know, like by 3 over 3 pretty much, right? We get 3 pi over 9. Which is pretty much like the same, right? Because this is a whole, pretty much. So it's like we're multiplying by 1. So 3 pi over 9, whole number, that works, right? And well, what if we get 0.5 now? So 0.5 over 3 times 3 over 3, 0.5 times 3, that's 1.5 pi over 9, right? And if we have 1.5 pi over 3 times 3 over 3, we would get 4.5 over 4.5. So the only whole number is this one. So that means that this point right here actually holds up as a center for a 9. So cool, we got our 9. So we can put in this one to be 9. And then, well, what if we also, we're trying to find, so 9 is checked. So we have 9, we found it. You can put a 9 there in that point. And it makes a lot of sense because if you think about it, that center of a triangle is actually threefold. So being 3 multiplied by 3, that makes it a 9. It makes a perfect sense. Now, if we actually, you know, combine these with more equilateral triangles as such, imagine that's a hexagon. the corner of this triangle is going to be 6-fold. So if we install a 5-fold, a 9-fold point there, it's not going to fit. It's gonna go out of whack. There are going to be lines that just don't meet where everything needs to meet. So it's still, that's what I love about this approach, that it just makes a lot of sense to think of, well, where could I put my 9? Well, you can put your 9 there, because 3 and 9 have a common factor. So it just makes a lot of sense. Alright, so we said that, and I kind of gave you a clue as to where we could find the 12. We could also put a 12 there, actually. So I'm going to take this away, so this sort of like what gives us the big clue as to where we can put in, which is this one. This angle retains to this one. So we found where to put our 9. Now let's look for where we can put our 12. So now we're going to be like, pi over 3 times, we got to go to 12, so it's 4. So that's equal to 4 pi over 12. We have here 1.5 pi over 3 times 4 over 4. That makes it 3, that makes it 6 pi over 12, and then 0.5 pi over 3 times 4 over 4 is equal to 2 pi over 12. So, fun fact, you need at least, so whatever you put into it, a pedal is going to be, it's going to cost you 2. So a pedal will cost you 2 pi. That's how much a pedal costs. A pedal is these shapes. So whatever base you're in, 2 pi is going to cost, So you see here, for instance, we have 1, 2, and 3. And that's a right angle right there. So if we say that each pedal costs 2 pi, then this is that one, isn't it? 6 pi over 12. 6 over divided by 2, 3. So that means that there's going to be 3 pedals. Each pedal costs 2 pi over that base. So for instance here we know that it's a 9 because we're working with that 3-fold point, and we have 1, 2, and we said that this one is going to be 3 pi over 9. So each pedal is 2, we take away 2, we're still missing a half. So 1 pedal, half pedal, 9. Because it's going to go 3 times around the center. Goddamn well should. No, this is going to go, well, technically 6 times, but it's half of an equilateral triangle. So it's almost as if we mirror this over here and then we mirror that over there. But there's like a way to mirror that thing. But that is a 3-fold minimal triangle. So yeah, there's that. So now the 12, we could choose, well, if we're looking at this one, because this is the one that actually has a 9 and 12 interacting. And we see that, well, we have only 1 pedal here. So we choose this one. So then our center for 12, we're going to write it down, that one maybe in red, just to distinguish them. Our 12 we're going to put in right here. And we're going to leave this one alone. We're not going to care about it. As you can see, nothing's happening in this right angle. But now we also might follow, I'm going to redraw this one. So okay, we found where to put our center of 12, and we found where to put our center of 9. And now comes the fun part. So I'm going to take this away. I'm going to leave this just to show you, like, when I say base 3, that means which polygon we got this from. So we got this from a triangle. Base 3, triangle. We're looking for the 12-9 pattern. And we're going to draw this triangle again. But we're going to copy it from that orientation. So it's going to look a little something like this in it. So this is the one that's a 9 right here. I'm going to write there actually 9. And over here there's going to be a 12. So this one in 12, this angle right there, we said that that's an angle of 2 pi over 12. And this one is going to be an angle of 3 pi over 9. So that means that this is going to be split into 3 parts. Like that. 1, 2, 3 parts. And this is going to be split in half. And so you see that they meet. And that's that point. Where this line meets that line. And then, well, what's hard to do, sort of, with a compass and straight edge, is that you now need to find the perpendicular line from that point toward the edge. So it's almost as if you need a line now that goes from here, from that point, goes off to the edge, meets it at a right angle, so it's perpendicular to the edge, and then that's your radius. So then you draw here a circle, and then these points of contact are where the star is happening. So we know that at that point, a star is going to be happening. Now the question is, which star are we going to put into it? And so I chose the 12.5, I believe. I think I chose the 12.5. Now my logic being that this line is actually perpendicular to the edge. It's not coming in and meeting at that point, so this point right there is not evenly spaced to this one. So this one is escaping from the whatever circle this is in. But this point isn't. So we can find that angle based on either the triangle or whatever, or we can find where this one's going to hit and draw a line that's parallel, that's perpendicular to it. So this one there is going to just like hit on this point, and it's going to go parallel to this purple line that we have here. So it's pretty much just going to go like, and then it gets mirrored, reflecting over here. And then as it goes, well, we're still missing that part of it, but we should also construct like this other side of this star. So it's almost as if this 9 line comes in. Now this is where it gets complicated and a little convoluted. If you're not initiated, this makes no sense. But if you are initiated, you're like, oh, well, damn, I'll be damned. And so you see that there's like a little pentagram almost, like that line goes over there, that line goes over here. This line gets mirrored. It goes down like so. Actually, this one doesn't go all the way. And this gets mirrored here, this gets mirrored there, I believe. We get half of, we get half of it. This one actually goes down there, and this one then comes back out. This one comes in here, it bounces back out. Gives us this weird shape over here. We got the star, this one bounces over here too, bounces over there. So we have our star sort of inside of the circle. As you can see, the top part of it is not inside the circle. My diagram might be a little there, but that's sort of how you can make different symmetries work together. And so we can use the base 3 triangle to get a 12.9, but we can't use a base 6. Now that's an interesting question. Why can't we use base 6 for this construction? So then if we, so we have this triangle. Well, I'm going to write here that's 12. This triangle with base 3, we can make a 12.9 work. Yay! And we're multiplying it by 3. That's a cool thing to think about. We can also like make 9.15 if we wanted to, because it still makes sense over here. No, 15, would it make sense? We just have to make this number be a whole number or not, but whatever, as long as we can multiply by something, and it has to be at least a half. It has to be at least a half. If it's a 0.25, like if you put in an 11 gon there, it won't make sense. If you put in a 16 gon there, it won't make sense. It has to be a multiple of 3 to make sense. You know what I mean? Maybe I don't even know what I mean. But now I'm going to look at the triangle for the hexagon. So this one's going to be base 6. And here I'm only going to make 12s interact. But still, it's an interesting exercise. So whatever base we're at, the center of the 6, so that's the center of my 6, that's going to be a 1, this one's going to be a 2, and this one's going to be a 3. Again, base 6, that means that it's whatever number we put in, pi over the base, pi over the base, pi over the base. As you can see, this one is a right angle because it's half of the base, so pretty fast, right angle. These two triangles are the same. We can divide these and make it base 6. Interestingly enough, even though they are the same, whatever number we're interpreting them in actually makes a difference. So we're looking at this one now. So we're going to apply a pattern of 12. Pretty much we're going to make a pattern of 12ness. So it'll be that example. And so what I'm going to do is I'm going to interpret all of them, all of these angles, I'm going to interpret them in terms of 12. So instead of base 6, not even like instead of, rather, it's not instead of, but we don't call it something, we call it something else. That's a pretty shitty example. But yeah, let's just make all these 12. So I'm going to redraw the triangle. I'm going to call this one now 2 pi over 12. We'll call this one now 4 pi over 12. And this one now 6 pi over 12. Now why? Well, because I'm simply multiplying it by 2. So this one I could say, you know, like pi over 6 times 2 over 2 equals 2 pi over 12. 2 pi over 6 times 2 over 2 is equal to 4 pi over 12. 3 pi over 6 times 2 over 2 is equal to 6 pi over 12. So there you can see that, well, this one I did great. So you can see how I got my angles for this triangle. Same angles, but now it's base 12. You know, same triangle, just base 12 now. Now all of these are actually going to be centers, well, except this one. This one's not going to be a center. But these two are. I'm going to take this away. And I'm going to write down that a pedal, where do I write this? This is important. A pedal costs 2. This is very important information. So whatever n is what star it's at. I don't know if that makes sense. But yeah, this is what a pedal costs. So if you have, for instance, a 6 pi over 12, how many pedals can you put into there? Well, 2 pi over n. So how many 2 pi's over 12 can you put into there? Or rather, how many times can you subtract 2 from 6? So that's 3. So you can see there we have our 3 pedals. We have here 2 pi, so how many times can we subtract 2 from 2? Only 1. So 1 pedal here, 3 pedals there. Awesome. And well, yeah, we don't have a center over there. But what's happening, if you'll notice, is that this line is coming down because it's a 2 now. And this one's divided into 6, so it's almost like, you know, this one comes down, this one will meet it, and this one will then go like 1, 2, 3, 4, 5, 6, yeah. Yeah. It goes off into this one goes off into here, which is also a matching point just as this one is, apparently. And then, yeah, this one kind of just like goes off, and then this one also does that same thing. So inside of these are going to be circles, so the circle also goes like a perpendicular line toward the edge, and there's a circle. Here is half a circle, but it will hit on the bottom part of this. We're not doing anything with the top though. And this one's going to go there. So pretty much it's like putting circles into this thing. These circles actually should touch. They should touch. They should. So inside of this circle is where this is happening. I'm going to break it down too much, but this is pretty much how we can make a pattern, or we can think of a pattern in terms of these minimum triangles. And we can also, by the minimum triangles, know how many petals we can put into each of them. Let me think of another example I might have here. Here, let me pull this one up. I'm going to pull this one up, and I'm going to pull this one up. So now we're in 5 territory. So I'm going to erase this. I don't even know if I'm over time here, but now I'm going to change things up a little bit. So we saw how to make a 9/12 from a minimal triangle of a triangle, and we saw how to make a 12 pattern. This one's from Cairo, as far as I know. I took a picture of this pattern when I went to Louvre many years ago. We're lucky enough to have gone. Thank you, God. And then we're going to look at these patterns, which this one's from Iran, if I'm not mistaken, very Iranian. You can see that, the hourglass shape and whatnot. And this is just canonical. This is one of the more typical patterns. Here I have it interpreted as this little triangle right here actually pertains to the minimal triangle of a decagon, while this triangle right there pertains to the minimal triangle of a pentagon. Pretty interesting stuff, wouldn't you say? Alright, so let's look at it. Alright, well, minimum triangle for 5 and 10. Alright, so let's break it down a little bit. Well, first off, How many petals are there? Well, first of all, we see that it's 1, 2.5. And that's a right angle right there. That is a right angle. There's no doubt in my mind that's a right angle. So what does that mean? It means that it's going to go 4 times. So it's going to go like 2.5. It's almost like this. 2.5, 2.5, 2.5, and 2.5. Right? 1, 2.5. 2.5, 2.5. So 5, 7.5, 10. Tenfold. Tenfold corner. And that's how it works. So that tenfold corner is either 2, you can look at it as a 2.5, but again, we saw that a petal costs 2 pi over n. So that has to be for 1, that's a 5 pi over 10. That's a 5 pi over 10 angle. Well, no, it's a 5 pi over 10. That's a half. Yeah. Ain't that nice? All right, look at this. Base 5. Wait, I just gotta look at the time. You just gotta look how long this is going to go for. We've gone on for, I don't know, maybe too long. Alright, really fast because then I can't even download the thing, so I have to do it again. And that's just sad. Alright, base 5, we look at that and we get a 1. Get a 1, 2.5, and 1.5. Looking at this one. It's almost like you can imagine this to be tucked. So we're going to install, now we're going to take away this. Again, looking at that. Give me just a second here because it's that center, and then if we have this one come in and this one, it's going to fill it up now. It makes no sense. It's not like it's tilted. That's the right angle there. No, so it's like, what? No, it makes no sense. Oh, I see. Makes more sense like that. And it's almost as if we are, in this case, doing this, and then like that, and then like this. This one actually goes all the way. It goes in half. Meets it there, goes up there. So this triangle, that makes sense. This triangle right here is this triangle from the base 5. And this little triangle right here is the triangle from the base 10. So we have a deck again. We don't have to draw the full deck again, but we can sort of imagine. In a deck again, we would have here again a 1, and then this one's going to be 5, and this one's going to be 4, because we have to add up to 10. So 1, 5, 4. And, well, we can also see how, well, if we mirror this, the same thing as a 4, that's a 5. Not 4. Okay, I'm obviously tired now because I'm screwing up on math. So it might be going a little bit too long in this case. But yeah, we're just going to do this. Okay, so we have here the minimal triangle for a pentagon. And this line is going to go in half. Well, we wanted to put a 10 pattern. Well, we can see here that we have, again, the 3 petals on a right angle. No, 2.5 petals on a right angle. So pretty fast we know that that's going to be a 10. What's interesting is that, well, we can change this all into 10 now. So if we change it into 10, this becomes a 5. This becomes a 3. And this becomes a 2. We see that the 5 share in common between these 2 triangles. Because, again, well, this is the minimum triangle for the 5, and this is the minimum triangle for the 10. What's interesting is how we can make sort of a combination of the triangles in order to get like a full rectangle. I think that's interesting, the way they can combine So for instance, we would get a 4 there, and then we're saying that we're putting the 3 angle right there, kind of like that. So this one's 3. And so this line is, we're saying that we want it to be, I'm sorry, actually this one, well yeah, 1, 5, 4, so this is 4. This is 1, we have to add up to 10, that's right. Sorry. Has to add up to 10, so 4, 3, that's 7, and we're missing 3, so we put in the same triangle. That's a 3, that's a 5, that's a 5, and that's a 2. And then here that's a 1, that's a 5, here's a 4, here's a 2, here's a 2. So a right angle has to add up to 5, so 1, 2, 2, 1, right? So 2 plus 2 plus 1, that's 5. We have a right angle there, that's a 5. Here a 4, and then this angle is going to be a 3. No. It comes in with that one. So yeah, it's 2, 3. So this one's 3, and this one's 3, 3, 3. That's 6 plus 4, that's 10. 1 is that one, this one's 2, this one's 2. So 1 plus 2 plus 2, that's a 5, like that one. 5, 4, 3, 3, 5. 5, and 5. So we pretty much substituted the angles pertaining to this particular rectangle, and we can find sort of a breakdown of these two triangles of the pentagon and the decagon. We can make them work together, and we get this shape. And so because we're working with a 10, we can also expect the 10 to work like it is. So for instance, this 2 is going to be, it means that it's going to be divided in half here. This 2 means that it's going to be divided. This 2 can match with that one, then we match that one. So we can put a circle inside of there, since these two centers, we're also saying that, right? Like this corner of the pattern, that's a center, and this corner of the pattern, that's a center. So from there, the lines are sort of shooting out, and they're meeting here. The radial lines are meeting there. So that's sort of where we can draw our circles. So the minimal triangles from the circle packing have a lot to do. But just as a fun fact, I mean not as a fun fact, but as an identification tactic, we can use right angles, or we can just count how many petals there are to find what symmetry it's in. And we can, well, especially when right angles come into play, or any sort of angle comes into play, we can sort of do a little quick multiplication and find what it is we're working with. So you can see that this, for instance, is inside of a circle. So it means that here there's a circle. We have these two lines coming in, and we just need these two lines now coming out. This one's actually going to come in there at a right angle. This one won't come in there at a right angle, but it's a nice little thing. Actually, no, this one actually does come in there at a right angle. Just like this one does. And then we can just simply substitute, because these 5 points, we can substitute these 5 points and put in a star system in there. Line would extend, line would extend, line would extend. Line would extend. I was reading Jay Bonner's book, and Jay Bonner insists that the polygonal method was used extensively. And although the polygonal method can simplify constructing on a big scale, these kinds of approaches I think are more mathematical and have a more intuitive, not intuitive, but it really does help, I feel, like dive deeper into them. So my throat hurts now. I haven't drank water in all the time I've been speaking. So I'm going to cap it here for now. So thank you for joining. I hope you enjoyed it. And yeah, I'll catch you in the next one. Take care. And yeah, oh, by the way, where is this thing? Wait a minute. Wait a minute. So I have here a paper. A paper with the name of the Patreons. Where is that paper? I want to thank the Patreons that make this possible. They're people that support the channel, support me doing these kinds of crazy things. Here we are. Support me on Patreon, so I want to thank them if they got this far, right? I want to thank Alenka Plaura, Virgit Schilling, Folderia, Sarah Gerskin Brewer, Shashi J, Anurag Agawa, Faidme, Irina, Jean Hollova, Mansabaya, Nathalie Simeon, Peter Keller, Surabi Koka, Usma Sayed, Amit Hindocha, Hannah Luger, JDC, Rui Qureshi, Shamina Haq, and Julia Antonova. So thank you for the Patreons, thank you for your support. Hope you enjoyed this little lesson, and I'll catch you in the next one. Take care, and bye-bye.